In this class, we're going to talk about a topic that's related to the kinetics from last time, but it's not exactly kinetics. It involves a lot more fields in science. And so this is the topic of reaction mechanisms. And I want to show you what these are by using a specific example. The reaction that you see on this page, O3, goes to O2, is what's called an overall reaction. It just shows you what reacts and what forms. It doesn't show you whether there's any steps that it goes through in the process. O3 is what's called an allotrope of oxygen. It's one of the elemental forms, but O3 is not breathable. It's a toxic molecule, and it's also what you find in the ozone layer, which absorbs the harmful ultraviolet light from the sun and keeps it from reaching the Earth's surface. Now, this reaction is balanced with a 2 in front of the O3, but that does not necessarily mean it's second order. We did that last class because we don't know the mechanism, and so it might not be second order. And because it's an overall reaction, it does not occur exactly as written. If it did, I showed the picture below on this page with the blue balls. If it occurred as written, two O3s would collide and out would pop 3 O2s in one step. But that's not the way people think the reaction actually occurs. And I wrote what people think is the mechanism at the top of this page. It actually occurs in 2 steps. We're going to talk about how scientists come up with these mechanisms and how they test them. But first, I just want to show you the characteristics of one. What people believe is that one O3 molecule actually breaks down into an oxygen molecule O2 and an oxygen atom. That's what the first step shows in the blue balls also. Then the oxygen atom that forms, as you know, oxygen atoms are extremely reactive. You never find them by themselves in nature. They're always bonded to something. So as soon as that oxygen atom is formed, it'll react with another O3, and that's the bottom reaction in the blue balls. The oxygen atom pulls one of the oxygens off the O3 and forms 2 more O2s. Now, I put slow on the first step, which is what would be expected, because O3 is a very stable molecule and it doesn't want to split apart like that, but if it does, the oxygen atom that's formed would be very reactive, and it would immediately react quickly with another O3 molecule. Each of these steps in a mechanism is called an elementary step because it's as simple as it gets. These steps are believed to occur exactly as written. I want to make a few comments about where you're going to see mechanisms again, because if you stay in science, you will. The first thing I wrote down is that, organic molecules, there are an infinite number of them. So in organic chemistry next semester, you're going to see lots of molecules. The thing is, there's also millions of reactions. What mechanisms do is they organize the reactions into types. See, each alcohol, for example, does the same kind of reactions by the same mechanisms. And so you can take millions of reactions and put them in one class. You talk about reaction mechanisms at the beginning of every kind of reaction that you discuss in organic chemistry. Number 2, I said that all of those biochemical pathways for synthesis and metabolism in biochemistry books, like glycolysis and the Krebs cycle and the electron transport chain, those are all mechanisms because they show the process one step at a time. So in order to understand biochem, you have to know those. The reason why they aid in drug development is that if you know the biochemical mechanism, you can pick a step that you want to interfere with or enhance, and you can develop a drug to do that in order to cure a disease or whatever. They also aid in improving drug synthesis, because if you're trying to synthesize a drug, if you know the mechanism, you might be able to change the reaction conditions so that you can synthesize it more effectively, faster, or more of it, or cheaper. And it's the same in industry. Industry makes money by producing products. If you know the mechanism of the production, you can come up with better, faster, cheaper ways to produce things. So a lot of people in science are interested in mechanisms, and you are particularly going to see a lot of it next semester in organic. I want to make sure you know that you do not have to invent mechanisms. These are things that chemists come up with through experience and through testing. The thing is that I will give you a mechanism and ask you questions about it. But what I want to tell you is the main thing that chemists do to test a mechanism they think is true is they will first of all do the kinetics of the reaction in the lab. In other words, they'll go through and do all of those things we did last class. They'll measure time courses and get all of those graphs, find out the order and the K value. And once you've done that, they consider that an experimental fact. It's been measured. There's no way to contradict it because it's just math. But if you want to verify that a mechanism you're proposing is correct, you need to know what the predicted rate law is for the mechanism. The mechanism steps, if you do it mathematically and combine them correctly, will give a rate law that's predicted by that mechanism. In other words, if this mechanism is correct, it has to give a rate law that you can figure out mathematically. You get the predicted rate law by combining the steps in the mechanism, the rate law for each one, mathematically. I'm going to show that you can write the rate law for each step, and then you go through a mathematical process to get the predicted rate law. There's actually only two kinds of steps that you see in typical reaction mechanisms. One is called a unimolecular step. It means that only one molecule reacts and breaks apart. The O3 reaction, that's the first one in the mechanism, is an example. You can write the rate laws for these steps by using the exponent in front of, or the coefficient in front of the substance as an exponent in the rate law. I told you that for an overall reaction, you cannot do that. But because an elementary step occurs exactly as written, you can write the rate law for the O3, for example, as rate equals K times O3 to the first. You're only allowed to do that if it's an elementary step in a mechanism. Another kind of a mechanism step is called a bimolecular step, which is where two molecules collide and react. The second step in the ozone mechanism is one of these, and you can write the rate law in this case as K times oxygen atom to the first times O3 to the first, because those are the coefficients. We're going to see a reaction mechanism later that has a bimolecular step where the same thing reacts with itself. NO2 reacts with itself. And because of the fact that these are NO2 plus NO2 can be written as 2NO2. So the rate law would either be rate equals K times NO2 times NO2, which is the same as NO2 squared. I would ask you to notice that reaction mechanism steps only have the reactants in them, not the products, because it's the reactants that are colliding, and so they're the ones that actually control the rate. There are sometimes termolecular steps in mechanisms where three things collide at one point, but they're very rare because it's a lot less probable for three things to collide with each other than for two to collide. And so we're not going to look at any termolecular steps because they're always very slow and they are rare. Next question I want to talk about is how do you get a reaction mechanism and verify it? The thing is this is not the same kind of a problem that we've been doing in this class where I ask you a question and I say if you follow these steps you'll get the correct answer at the end. Coming up with a mechanism is a creative process. And what you could do, for example, is that you might come up with, if you were meeting with people in your lab, you could write down what you think a mechanism might be for a reaction. And if you're good chemists, you could come up with all kinds of possibilities, but you hope that the right one is among the choices. And then what you do is you eliminate them by a process of elimination. The mechanisms that you propose have to meet two requirements first. First of all, the elementary steps have to add up to the overall reaction. And secondly, the mechanism has to predict the correct rate law. Let's suppose a research group writes down what they think are 6 possible mechanisms for a reaction. You can't take a little camera down and watch what the molecules are doing. So the only way you can do this process is to first of all try and then eliminate the possibilities. Suppose that mechanism 1 and 2, when you add the steps, they don't even add up to the overall reaction. That's obviously a requirement because it can't be the mechanism if the steps don't add up to what you're studying. So you can eliminate those 2 as possibilities. Suppose that you take mechanisms 3 and 4 and combine the rate laws for each step to get the predicted rate law, and you find out that they predict a different rate law from the one you found in the lab. You then have to throw those 2 mechanisms out because you know that the one that you determined in the lab is the one that's considered a fact. Even after doing those 2 steps, you still are not down to 1 possible mechanism, but you have eliminated ones that are not correct. You then have to do more experiments to figure out which, if either, is the correct one, and we're going to discuss those kind of experiments also. Everybody knows how to add reaction mechanisms, and we're going to do a couple of examples of that. But the second principle, how do you determine a predicted rate law? That is a very difficult mathematical problem with lots of different possibilities. That could be a whole course in kinetics. I don't want to do anything that complicated, but I want to show you one possibility that is the main one and that you can use to get a predicted rate law easily, which I'm going to call the basic principle for reaction mechanisms. You have to believe the statement that I wrote there first. An overall reaction cannot be faster than the slowest step in the mechanism. What that means is, let's say there's 4 steps and one of them is very slow. You cannot get the reaction over with until you get the slow one over with. It's like somebody driving in front of a bunch of cars, and the cars are strung up all behind them because the front car is going very slow. Nobody behind him is going to get to the destination until the slow car gets there. Now, the slowest step in a mechanism is called the rate limiting or rate determining step. When you're trying to do organic chemistry mechanisms or biochem mechanisms, the rate limiting step is the first thing you look for because it usually determines how the reaction happens. Now, if the first step in the mechanism, though, is the slowest step, you can show mathematically that the rate law for that step, the slow step, is the same as the predicted rate law for the entire mechanism. In other words, after you get that slow step over with, the others are so fast that they don't affect the rate. But if the slowest step is not the first step, you have to go through a lot of mathematical processes, because the reactions before the slow step can be involved in the rate law because they back up behind it. We don't want to do that case. We only want to do case 1. So I would like to show you how the 2 steps work with the ozone mechanism that we predicted. Now, if you write those 2 steps, they have to add up to the overall reaction, and they do. Everybody knows how to add reactions. Everything on the left goes on the left, everything on the right goes on the right, and you cancel anything that's the same. It's just like a redox reaction. But the oxygen atom is what's called a reactive intermediate. The reason it's reactive is because they're always very unstable, and they react right away. And it's called an intermediate because you don't put it in. It gets generated in one step and used up in the next step. And so you also do not see it in the final reaction. It's only present during the interim part. Every mechanism has to have at least one reactive intermediate because that's what continues the chain. In this one, the first step produced one, and it's used up. In some mechanisms, then, that one will produce a second intermediate, which will do a third step, and the third step will produce another one, which will do a fourth step. But the idea is that every mechanism has to have at least one of these to continue the steps. Now, the second requirement is that the mechanism predict the correct rate law. We've already written the rate law for each one of those steps. You use the reactants and the coefficient in front of them for the power. Since we believe the first step is the slow step, the rate law for that step will also be the predicted rate law for the mechanism. Does the first step have to be slow? No. You could test and see what the rate law would be if you made the second step slow, but that wouldn't be very likely because we already talked about the fact that O3 doesn't want to break down very easily, and so it is probably the slow step. How do you use that to test this in the lab? Well, the predicted rate law is K times O3 to the first. If you go and do the kinetics for this experiment in the lab and you find that the rate law really is K times O3 to the first that you find in the lab, you can say that this mechanism is possible because it gives you the same predicted rate law as what you found in the lab. But if you go in the lab and find out that the rate law is actually second order in O3, you can then say we have to throw out this mechanism because it gives you the wrong predicted rate law, so it can't be correct. Now, even if those 2 tests are valid, that doesn't prove the mechanism. You have to do many further experiments to verify it. And the thing is that even no matter how many experiments you do, you can't be sure the mechanism is correct, because the truth is that there could always be more steps. You can usually find the minimum mechanism, but you really can't absolutely find all the steps. That's the reason why they never call a mechanism proved. They only call it well established. But the mechanism is like a model in science. A model is for making predictions, and if you can predict behavior based on the model, the mechanism, it's very useful. Now, this might all sound kind of confusing, and so what I want to do is tell you what steps I'm going to ask you about, or the questions I'm going to ask you about mechanisms. First of all, I want you to be able to add mechanism steps and see if they add up to the overall reaction I give you. Secondly, I want you to identify the substances in the reaction that are reactive intermediates. I want you to be able to write the rate law for each elementary step. And I want you to use the basic principle of reaction mechanisms, that if I give you a mechanism and tell you which step is slow, especially if the first step is slow, I want you to tell me whether the mechanism is consistent with the rate law that you find in the lab. In order to give you an idea about how chemists might actually do this, I want to show you a real reaction that people have experimented on in the lab. The CO plus NO2 reaction that I show you there is the same one that we used last class to demonstrate orientation of the fact that molecules have to be facing in the right direction in order to react. This is the same reaction we used for this slide last time. Now what the experimenters did was they ran this reaction at several different temperatures. And what they found is that 225 degrees C is a cutoff. Above that temperature, the rate law is first order in both CO and NO2. But at low temperatures, the rate law continued, but the rate law changed. The rate law became second order in NO2, and CO was not involved. It was zero order. So the chemists came up with two mechanisms that they proposed might be happening at those temperatures. Mechanism one that they proposed is actually what's called a single-step mechanism, where the reaction is the actual mechanism. So there's only one step, so that it is also an elementary step, and it occurs exactly as written. Mechanism 2, they proposed that NO2 molecules could collide with each other and first trade an oxygen. The NO3 that's formed, we know from chemical studies, is extremely reactive. You can't even isolate it as a pure compound. So if it does form, it would immediately react with a molecule of CO to give you the product CO2. And the thing is, the first step would definitely be the slow one, because NO2 molecules are stable and they don't want to trade an oxygen. All I want to do with these two mechanisms is I'm going to tell you that these are the two that people believe happens. I want to match each mechanism with the correct temperature. Now for mechanism 1, there's nothing to add because there's only one step, so it's the overall reaction. But the rate law predicted by the mechanism, since there's a 1 in front of each substance, is going to be NO2 and CO are both to the first power. Now we want to do the two steps for mechanism 2, and I wrote the steps here. If you add those two steps, they do add up to the overall reaction, but there's two things that cross out. NO2 is not considered an intermediate, so things are not an intermediate just because they cross out. They have to be generated in one step and used up in another. The reason why NO3 then is an intermediate is I didn't put it in. It got generated in one step, and then it got used up again, so it does not appear in the final equation. It's only in the interim part. NO2 is not an intermediate because we put it in. It's one of the reactants. And it also appears in the final equation. So that does not qualify as an intermediate. In order to determine the predicted rate law for mechanism 2, all we have to do is to look at the two steps and realize that it's predicted that the first one would be slow. So the predicted rate law will be the same as the rate law for the first step. Now we're ready to match the mechanisms with the correct temperature. According to the experiment, the high temperature rate law was CO2 and NO2 to the first. As you can see, that is the rate law that was predicted by mechanism 1, and so mechanism 1 is probably the one that occurs at high temperatures. The low temperature rate law, NO2 squared, is the one that's predicted by mechanism 2, as it shows in this slide which we looked at. That's the reason why people have come to the conclusion that this mechanism occurs as according to mechanism 1 at high temperatures and mechanism 2 at low temperatures. The next thing you want to ask is, does it make sense? If you look at the high temperature reaction, CO2 and NO2 are going to be moving very, very fast, and they're going to have enough energy to just smash into each other and produce the products in one step. That makes sense. Now, as you lower the temperature, what usually happens is that molecules move slowly, and so they finally get to the point where they don't have enough energy to get over the energy of activation bump. When that happens, the reaction stops. But what happened in this case is that in mechanism 2, it found an alternate pathway so that the reaction could still continue. Mechanism 2 involves the creation of a reactive intermediate. So it made a very reactive molecule, NO3, that was able to continue the next step and still produce the products, even though the reaction was probably slower. Now the thing is, you do this all the time when you're trying to drive. Let's suppose that you have a way that you go to school. If there's no traffic, you get here in a certain time. But if one of the places on your route is blocked by an accident or construction, you probably also have a way that you can drive around that spot and get to school. It'll take longer because it's an alternate route, but you still get to the same place. That's what happens with mechanism 2. Now, the thing is that the first step in mechanism 2 is very common type of reaction in organic. It's called an activation step. A lot of times reactions can't occur exactly as written, but if you do an activation step first, where you produce a reactive molecule, then the reaction can continue. You will definitely see that again in organic. The question is, what kind of an experiment could you do to prove that these are the mechanisms? I think you would probably agree with me that for mechanism 2, since NO3 you did not put in, and it's also not in the products, if you could demonstrate that NO3 was present during the reaction, that would probably be strong evidence for that mechanism. Chemists can do that by what they call a trapping experiment. You can put in a molecule that only reacts with NO3. Everyone knows that in chemistry. If you see the molecule after the reaction that comes from the reaction of NO3 with what you put in, the only way to explain how you got that would be if NO3 was present. So the NO3 is trapped as it's formed. Sometimes you can find intermediates that will absorb light, and you can do this by spectrophotometry. There's different ways to try to isolate to try to trap the reactive intermediate. People have come up with some of the most ingenious experiments done in chemistry to try to prove mechanisms. I'd like to do a section on it, but I don't want to at the present. But just imagine trying to figure out a mechanism like glycolysis or like the Krebs cycle. How in the world did they do that? That's a fascinating study. The thing is that even if you do these kind of experiments that tend to indicate that the mechanism is correct. Remember, all we can get is the minimum mechanism, and so they still only refer to it as well established. The next thing I want to show you is what a catalyst does to a reaction. We already looked at this last time. The catalyst lowers the energy of activation, but I also said in the top line that it speeds up the reaction by increasing the number of steps in the mechanism. Now you might think if you get more steps, the reaction is going to go slower, but remember, it's not the number of steps that controls the rate, it's the slow step. What catalysts do is they split the slow step into pieces, and each of the pieces has a lower energy of activation, so the entire reaction is faster. The reaction of H2O2 decomposing to oxygen happens without a catalyst, but it's very slow. So in this experiment, we're going to add a catalyst, Br minus bromide. What people believe happens is that the mechanism when you add the catalyst is that the bromide reacts with H2O2 and produces bromine element dissolved in water. The bromine element is extremely reactive, and so it reacts in the next step with another hydrogen peroxide to produce the oxygen. The Br2 production is an activation step. Now, chemists know that Br2 is a very, very reactive substance. It's orange when it's dissolved in water, but when it's in the pure state, it's a very dark red liquid. And if you breathe the gas in, it burns your lungs out. And if you get a drop of it on your skin, they say that it goes all the way to the bone without stopping. And the wounds take a long time to heal. So it's a very reactive element. The next thing that we want to do then is determine whether these two steps add up to the overall reaction. I showed in this slide that the two steps do add up, and there's actually three of the things that cross out, but only one of them is a reactive intermediate. The other two are catalysts, and the next slides will explain that. The reason the Br2 is an intermediate is that you did not put it in, and it gets generated in one step and used up in the other, so that it it's not in the final products. The other two are catalysts because you put them in. Br minus and H plus is already present because H2O2 is a weak acid. They get used up in the first step, but they get regenerated in the second step exactly as they were. That's what a catalyst does. It doesn't look like it's changing, but it gets involved in the reaction to be used up and then regenerated. You don't even need a trapping experiment in this one in order to demonstrate that the intermediate Br2 is present. This is a picture of someone taking concentrated peroxide and adding sodium bromide. So the Br minus in the first step goes to Br2, which is orange, and you can actually see that happening. And of course, the reaction mixture would bubble more as it's doing it, as oxygen is released. But then by the end of the reaction, the bromine goes back to colorless bromide. That's how a catalyst works, and you can actually see the intermediate when you do this reaction. So that's really all of the things I want to talk about related to kinetics, but now we're going to have to start the topic of thermodynamics. Now you know that kinetics is the rate of reaction, but we think mainly of thermodynamics as being related to the position of equilibrium, or the KEQ value. And I want to show that kinetics and thermo are really separate from each other in a lot of ways. The reason why the thermodynamics is considered to involve the KEQ, or the position of equilibrium, is because there's a mathematical relationship between delta G, which is the main function in thermo. It's called Gibbs free energy, and that's related to the equilibrium constant. We're going to look at the equation later. The thing is, delta G is used by all kinds of fields in science, primarily engineers. What delta G tells you is, does something happen or not? You can calculate, for example, a delta G for a beam in a skyscraper holding up the weight of the building or cracking and the building falls down. I mean, that's an extreme example. But that's the kind of a reason why physicists or engineers are interested in it. Molecular cell biologists are interested because delta G is what tells you primarily whether you have enough energy, for example, to make an ATP molecule, or do you have enough energy to transcribe a gene, or some other questions, and it's dependent on delta G. And in chemistry, we're interested mostly because of the relationship to the equilibrium constant. Now here I showed you two reactions. This is the potential energy diagram type that we looked at last time. If you look at that first reaction, the products are going to be favored because they're at a lower energy. You're going to get a large K. This is what you call favorable in thermodynamics. But just because the reaction is favorable, it doesn't mean that it's fast. That reaction is going to be very slow because the energy of activation is so large. The thing about that is the molecules want to get over the bump to get down to the lower energy, but it's kind of like they look at this big hill in front of them and it slows them down from getting there. So favorable does not mean fast. The reverse is also true. I showed you that in this one, the reactants are favored, and so they're not going to react very much because there's going to be way more reactants than products. But in this one, it's going to be very fast because it's a small energy of activation. So it sets up an equilibrium right away, but you don't get any product. You can have any combination of these two. You can have favorable reactions that are either fast or slow, and you can have unfavorable reactions that are either fast or slow. Kinetics and thermodynamics, you have to look at both in order to understand a reaction. I want to give you an introduction to how thermodynamics works. The problem with it is thermodynamics can almost be more like a philosophy as much as it is a science. It's how the universe operates. And in physics, I talked to some physics teachers. They do all the math that we're going to do and even more. The thing is, they don't really try to give much of a physical meaning to what the different functions are. We have to, because if you don't understand what the meanings are, they don't really mean anything too much in chemistry. The field of thermodynamics was discovered when people were trying to make faster steam engines. The steam engines in the mid-1800s would only go about 100 miles an hour because if they tried to get them to go faster, the steam chamber would explode. And so this field was developed trying to make faster engines, and it quickly developed into making cars because that was in the late 1800s. So this field was discovered for very practical reasons, and Gibbs and Helmholtz were the two that came up with it. That's why it's delta G. I want to show you, first of all, what the basic concept is in the field, and that is what's called spontaneity. If you take two reactants and two products like I have in equilibrium, and you go in the lab and mix random amounts of the four, no set structure to it, whatever you feel like. According to thermodynamics, there's only three possibilities. You might have picked concentrations that are already at equilibrium. It's not very likely, but this is the state where everything tries to get to if it's not at equilibrium. So there won't be any change in concentrations because the reaction is already at equilibrium. This is the state that we've been calling Q equals KEQ. The initial already is at equilibrium. The second possibility is that you might have picked too much A and B to be at equilibrium. So you're going to have to do what's called shifting to the right to use up some of the A and B and produce some of the C and D, and then you stop when you're at equilibrium. This is our case that we've been calling Q is less than K. When Q is less than K, you shift to the right. This case is the case that chemists call spontaneous as written, or in the forward direction. Spontaneous in English just means you get up and do it. No planning. That's what happens. It just goes the way it's written. But the reverse could have happened where you picked too much C and D. So in reaching equilibrium, the amount of C and D is going to go down, A and B is going to go up, and that means you're shifting to the left. This is our case which we called Q is greater than K. This is the case that's called non-spontaneous. You can also consider it spontaneous in the reverse direction. The thing is that the problem with it is in chemistry the reactions are reversible. Now in physics, a lot of times, physics will tell you that if something is spontaneous, the process happens. If it's non-spontaneous, it does not happen. There is really no contradiction because what it is that chemical processes are reversible, but classic physics is not. Classic physics is one way. So if a process is not spontaneous, it would prefer to go backwards, but there is no backwards. And so nothing happens. But in chemistry, what it is, it depends on the way you write it. If you write it so that it shifts to the right, that's what's called spontaneous. If the reaction actually goes in the reverse direction from how you wrote it, that is non-spontaneous. The reason why classical physics is not reversible, suppose you shoot a bullet out of a gun, and they ask you how high does the bullet go, how fast is it traveling, what angle did you shoot it at, how far away from you does it land, all these kind of physics questions. But I guarantee you that the bullet is not at the end going to come up off the ground, follow the same path, and go back into the gun. See, classical physics is irreversible. Now here we have that thing that I copied called the box. And the thing about it is Q and K tell you which direction a reaction shifts. Well, so does delta G. And that's the reason why you would expect them to have a math relationship, and they do. These are the signs of delta G. In the previous class on kinetics, I told you don't have to worry about the sign. If you get a negative in front of something, just take it off. In thermodynamics, I'm going to tell you the exact opposite. You have to know these signs like exactly for every function because this is what they mean. This is what thermodynamics means. So you really need to know the meaning of the signs for each function. Anytime you calculate a delta G for a process and it comes out 0, that means you're already at equilibrium. If you calculate a delta G and it comes out negative, that means the process will be spontaneous. And if you calculate delta G and it comes out positive, that tells you that the process goes in the reverse direction in chemistry. It's non-spontaneous. The thing that Gibbs and Helmholtz are given credit for is discovering that delta G actually depends on two other terms. One of them is delta H, which is enthalpy you studied in 131. This is the heat of a chemical reaction. H actually stands for Helmholtz, but everybody thinks of it as heat because who remembers Helmholtz? Anyway, this is exo and endothermic, and that's part of the delta G. But it also depends on another function, which a lot of times people don't look at until they're in physics. Delta S is called entropy, and most people think of entropy as being, as a analogy, it means disorder. It has a higher entropy if it's more disorganized. And that is actually a statistical mechanics concept, because statistics has something to say about disorder. What thermodynamics points out is that everything tries to get to a higher entropy or a higher state of disorder. And the reason is that there's always more ways for something to be disorganized or messed up than there are for it to be organized. I showed you this with 4 marbles. This is a simple example. If I define order as being all 4 marbles are touching, there's 4 possible ways that the marbles cannot be touching. And all of those 4 possibilities are disorder. Now, imagine that you started with 10 marbles. Wow. Imagine all the different disorders there would be. And so because there's more ways, entropy always tends to increase. I want to talk about each of the terms separately, so we're going to talk about the enthalpy term, or delta H, first. I showed carbon burning in a grill, for example. That is exothermic. The heat is given off. And you remember from 131 that the delta H for exothermic reactions is negative. I'm going to explain why that is in a minute. But I just want to say that this is what an exothermic reaction looks like. You write the heat as a product because it's being produced, and the reaction vessel, like the grill, gets hotter. You also know from 131 that delta H is negative. The thing is that the way we measure heat is in what's called kilojoules. I'm going to show you that joules are a physics thing I don't want to talk about. You can express either work, energy, or heat as joules. Kilojoules are 1,000 joules. All I want you to know about it is that's how we measure heat. But the third point here is the most important for us. Enthalpy has to be, if you run the process in physics at constant temperature and constant pressure. But in the lab, we usually do that. The beaker is open to the air, so the pressure is 1 atm. And we usually run it at either room temperature or a boiling water bath or something, so the temperature is also constant. The most important for us is that delta H has to be for the number of moles in the balanced equation. For example, if you burn 1 mole of carbon, it produces 394 kilojoules. If you burn twice as much, it produces twice the heat. And so it has to be for the number of moles in the equation. This slide shows why delta H is negative for exothermic. In any thermal problem, there's always 2 parts. There is a system and a surroundings. Those make up what they call the universe of the problem. Heat cannot get in or out of the universe in a physics problem, so the energy inside is constant, but it can be transferred. Whenever you assign the negative or positive to a function, you always look at it from the perspective of the system, not the surroundings. See, the reaction in this case is the system. The heat is coming out into the surroundings. So what's happening to the heat of the system? It's going down. That's why delta H is negative. The reason you want to call it positive is because when you're standing by a grill, you are the surroundings. Well, you don't do it from your perspective, you do it from the perspective of the system. The only thing this shows is that there is a conversion between calories, which is a chemistry thing, and joules, which is mostly a physics thing. I don't even want you to know the conversion. I just want you to be familiar with the fact that we use kilojoules to measure heat. Now you know that endothermic reactions occur and they absorb heat, and that means that the delta H is going to be positive. So I'm showing an example of that. In these reactions, the reaction vessel gets colder. You can actually feel it getting colder if you're doing it in a test tube or something, and the heat is written as a reactant because it's being absorbed. The delta H is positive because the system is absorbing heat, but you can say the same thing that we said for exothermic. Delta H has to be for the number of moles in the balanced equation. So since 2 moles absorbs 198, 4 moles would absorb twice as much. Now here's a few things that you wouldn't know unless somebody told you. So this is conventions in thermo. They consider room temperature to be 25 degrees Celsius, but you can't use Celsius degrees in thermo because Celsius does not have absolute zero as 0. You have to use what's called an absolute temperature scale, and the one that we use is called Kelvin. Kelvin actually has absolute zero as 0. Absolute zero is the coldest temperature there is. And you learned, you can't get there. And you learned in 131 that in order to get Kelvin, you have to add 273 to the degree C, because absolute zero is negative 273 point something Celsius. I'm not even going to make you remember to do this. I'm just going to give you Kelvin temperatures. I don't want you to just get problems wrong because you forgot to add or subtract 273, but I'll tell you, room temperature 25 degrees C is like 78.5 degrees Fahrenheit. I think these guys must have been hypothyroid or something, because to me that's not room temperature, that's a pretty hot room. If you look at the symbols, a lot of times there'll be a little superscript circle, and that means standard conditions. The subscript means the Kelvin temperature. You're running it at 298. So what are standard conditions? This is not very tough to remember. Standard conditions mean everything is 1. That's not too hard. It has to be 1 atm gases, 1 molar solutions, and what it means to be in the most stable state is, if, for example, if you had a piece of iron, it's a solid at room temperature. You're not going to have any standard iron at room temperature that's a liquid. It's whatever it is at that temperature. Now you can calculate the delta H for any chemical reaction by using a table. This table is a list of what are called enthalpy of formation values. What the enthalpy of formation is it's how much heat is gained or lost when you make 1 mole of a substance from the elements. And so if you look at the 2 reactions I have there, you're making 1 mole of the substance. You can even use fractions in balancing for this particular case. It doesn't mean a half a mole, or it doesn't mean a half a molecule or something of Cl2, it means half a mole. The reason why they want to measure these is because you can use these to calculate delta H for any reaction. And you have a table of these, which is table 6, which you're going to use for all your problems. This is page 19 from your textbook. There's 3 columns, delta H, delta S, and delta G. And also the substances are in alphabetical order by symbol. And here is the back of that table. It just continues. And I pointed to KClO3, which for delta H has negative 397.7. That's the number I had written by it. And N2H4 liquid is plus 50.6. That's the number I had for that. Now you have to understand that heat is relative. it's not an absolute quantity. You can only measure heat by measuring how much is transferred from one substance to another. There's no place in the universe that has zero heat. So you have to measure it relative. And what chemists have chosen to use as the standard is the elements. So any substance that is in the element form has delta H of 0. And I showed you a couple of these in the table. I2 is a diatomic element. The delta H is 0. K solid is not a diatomic one, but it's the delta H is 0. You can use the delta H's in the table to calculate the delta H for any reaction. You probably did this process in 131. Most people did, so I want to review it. You remember that in physics, anytime you have a change, it has to be final minus initial. In a chemical reaction, the final is the products. So what you're going to do is add up all the delta H's for the products minus the sum of all the delta H's for the reactants, and that'll give you the delta H for the reaction. I want to use the example of the reaction that I have written here. If you want to calculate delta H, you have to look up the amount or the number for each substance in the table. There's no way around it. You just have to do it. And for water, you have to watch it because water can be either a gas or a liquid at room temperature. So make sure you're using the one for what's in that equation. One way to do this, and I always do it this way separately, you can get a number for the products. Remember that the number in the table is per mole. And so since there's a 4 in front of the NO2, you have to multiply 4 times the number, and then the moles cancel. So for the products, you're going to take 4 times the NO2 number plus 6 times the H2O number. And when you add, you get a number for the products. You then do the same thing for the reactants. 4 times the number for ammonia, and oxygen is an element, so it's 0. When you subtract these, you end up with negative 1133.6, and you have to watch the signs. Minus a negative is positive. The negative delta H tells you that this reaction gives off heat. It's exothermic. But you cannot tell from only delta H whether the reaction is spontaneous or not. It's true that delta H negative tends to make reactions spontaneous. It's called the favorable sign because everything likes to give off energy and reach a minimum. But you know that reactions with a positive delta H do occur. They're called endothermic. The reason why that happens is because there's another term. You have to take into account the delta S also. Even if the H is good, the delta S could be so bad that the reaction still comes out and non-spontaneous, or vice versa. So only the delta G is the final answer to spontaneity. You have to know both H and S. So we need to talk about the S term next. The entropy term is actually based on or related to the second law of thermodynamics. There's actually 6 laws of physics that people believe the universe operates according to. And there's 3 Newton's laws of motion first. For every action, there's an equal and opposite reaction. There's the one about inertia. Body at rest tends to remain at rest till you act on it with a force. And there's also the one that gives you the equation F equals ma. A constant force produces a constant acceleration, however you want to say it. There's also 3 laws of thermodynamics. The first one is called conservation of energy, that the energy of the universe is constant. You can apply that to a chemical reaction in that If you add up all the kinds of energy on one side of the arrow, it has to equal all the kinds of energy on the other side, because you can't produce or destroy energy in a chemical reaction. The second law of thermodynamics is the one that has to do with entropy. I don't know if entropy came from the law or if the law came from the discovery of entropy, probably a little of both. There's a bunch of different ways of saying each one of these laws so that human beings can try to understand it, but there's only one mathematical way to express each of these laws. But I'm going to try to give you some of these statements so that it gives you a better idea of what they mean. One way to say the second law is that all systems have a natural tendency to proceed towards a state of maximum disorder. Another way that they sometimes state this law is that for any spontaneous process, the entropy or disorder of the universe increases. And we already talked about why this is. There are statistically more ways for something to be organized than disorganized. I'm sorry, it's the exact opposite. There's more ways for something to be disorganized than there is organized. Therefore, the increase in delta S, or the positive sign, is the favorable one, and the negative S is the unfavorable one. Do you actually believe this law? I said, all you need to do to observe this law is to look at my bedroom. If I organize it one day, get everything hung up right, everything's off the floor, 3 days later you can go in my bedroom and it looks like one of the battles from the Korean police action went through my bedroom. Things do not get more organized, they get more disorganized. If you throw note cards out of an airplane, they are not going to spell something on the parking lot underneath. There's a finite probability of that, which is essentially zero. They're going to fly all over the place. Things just tend to get more disorganized. But you have to remember that delta H can be the opposite of S, and so it can cause the opposite effect from what delta S predicts. I want to show you that there's a way to sometimes figure out delta S's without even calculating. Sometimes I just ask you, figure out what the sign of delta S would be for this process. And I want you to know three principles. First of all, the difference between solids, liquids, and gases. Solids definitely are the most organized. They're in crystals or molecules, solids. Gases have the most disorder. They're very high entropy because it's molecules bouncing around in space. Liquids are in between. So I showed a reaction where you can run electricity through liquid water and split it into the elements, the two gases, and this is called electrolysis of water. You would consider liquid water to be a state of order because it is much more orderly than gases. The gases on the other side would be considered disorder, and any time you go from a state of order to disorder, that is the favorable sign or positive for S, because everything tends to proceed towards disorder. If you wrote the reaction, though, in the reverse direction, now the delta S is negative. Depends on how you write it. The second principle I want you to know is that anything that goes from undissolved to dissolved increases in disorder. If you look at what I did here, I put sodium chloride in water. That's pretty organized. All the sodium chloride's in one spot, all the water's in one spot. But when it becomes dissolved, now it's a bunch of ions floating around, free from each other. So you're going from a state of order to disorder. Now that means that everything tends to dissolve. So the question is, why does everything not dissolve? Because there's another term. The delta H for dissolving can be so bad that it overwhelms the good S and keeps the thing from dissolving anyway. That's thermodynamics' answer. Now, you could spend your whole career trying to figure out why the delta H is bad for something, but the answer in thermodynamics is simply that it is. The third one is that more gas molecules have more disorder. What I mean by that is, for example, in the reaction I showed, there's 4 gas molecules on the left and 2 on the right. The ones on the left have more disorder because there's more molecules. It's pretty easy to see why more molecules have more disorder. I drew it in the bottom. I drew 4 pairs, which is what you start with. And you have to push the pairs together into piles, into 2 piles, and you have to split the green ones and the yellow ones in order to make the 2 piles. So the 2 molecules are much more organized. And because you're going from disorder to order, the S is negative. If you wrote the reaction in the reverse way, though, the S would be positive. Now, I want to show you that in the table, the S is not the same as the other 2 functions. There's no delta in front of the S. I left the delta off the S purposely for a particular reason. There is such a thing as absolute entropy. And that is because of the third law of thermodynamics. I said, now, how do you like that? We talked about all 6 laws of physics in a chemistry class. When was the last time you ever took a physics class that talked about 6 laws of chemistry? Like, chemistry is the superior science. What could I say? But anyway, the third law of thermodynamics says that you can't reach absolute zero in the physical world. Negative 273.15 or 6 or whatever it is. Now, that doesn't really explain why. I like the statement above, which I copied out of my physical chemistry book from college. It says that the entropy of a perfect crystal at absolute zero is 0, which means no disorder. If you could get to absolute 0 and you could get a perfect crystal, there would be no disorder. The molecules are not moving and they're in a perfectly organized state. Why can't you get to absolute 0? You can't get a perfect crystal. Every real crystal has imperfections in it, but I can tell you that even if you could get a perfect crystal, you still cannot reach absolute 0. See, all 6 of the physics laws depend on each other. That's how the universe works. If you change one, all of the other ones are wrong. You just can't change anything. They're a unit. They depend on each other. If somebody all of a sudden reached absolute 0, you'd have to throw out the other 5. Now, the reason this is important is that the delta S is really 0 at absolute 0. That's if you measure the same substance at a different temperature, that's not relative. You are measuring the S compared to a real 0. When you're comparing to a real 0, that's not a relative function. That's what's called in physics an absolute function. If you look at the entropy values, if you increase the temperature above absolute 0, obviously the entropy is going to increase. The molecules start moving, they start vibrating, and if you look at the S values in table 6, they're all positive, and elements are not 0 because they're being compared to themselves at absolute 0. So here you can see that all the delta S's in the center column are positive. And I showed the 2 elements that we looked at before. The H and G are 0, but the S is not. even for elements, the S is positive. You can calculate the S for a reaction exactly the same way as you do the H. You take the sum of the S's of the products minus the reactants, and it gives you the entropy for the entire reaction. Here's the same reaction we looked at before. I wrote all the S values from the table down, and I took the coefficient times the number for the products, the same for the reactants, and subtracted them. And we ended up with a negative S. Now, I always split the products and reactants, and there's a reason, because there's a danger in doing it all in one string. And students do that all the time. So let me show you what the danger is. If you try to do it in a complete string like this, people will subtract the first thing from the reactants and then add the second one. But that's not what it's supposed to be, and you'll get the completely wrong answer. But if you put the reactants in parentheses, now you're going to subtract both of them, and you get the right answer. You can't tell whether the reaction is spontaneous or not from the sign of S any better than you could from H, but you do know that the reaction goes from disorder and becomes more order because that's what the negative S means. You could have predicted the negative from one of our rules. You know, the more gas molecules have more disorder, so when you go from 11 to 10, the delta S will be negative. Now for the reaction we've been doing then, one, the delta H is favorable, and the other, the delta S, is unfavorable. So we still don't know whether the reaction is spontaneous. So we will not know until we get delta G, because delta G gives the final answer. And this is the equation that relates them. This Gibbs equation may be one of the most famous equations in science, because what does delta G tell you? It tells you whether something happens or not. I think you would agree with me that if you know what happens and what doesn't, you know a whole lot of things. And so delta G is calculated by taking the delta H minus the Kelvin temperature times delta S. And you already know that delta G is the final answer because we talked about the symbols or the signs. Delta G negative is spontaneous, positive is non-spontaneous. So now we can plug those two numbers from the reaction we're doing and find out what delta G is. When we plug in the H and the S and a temperature of 298 for the Kelvin temp, you get negative 1100.2. So we now know that the reaction is definitely spontaneous as written. You can calculate delta G from that equation, but there's another way to do it. If you're at 298 Kelvin, you can calculate delta G from the third column in the table exactly the way you did for H and S. You have to understand, though, that the only temperature that the delta G's are valid at is 25 degrees or 298. If you want to get it at a temperature other than that, you have to talk about how you do that. So I took the third column values and looked them all up in the table for the reaction we're doing. And when you do the products minus reactants, you get the same answer with an experimental error. And the thing is, you can do the 298 problem both ways, and it serves as a check to make sure that you didn't make a mistake. Since the delta G is negative and it's the final answer, we now know that the reaction is definitely spontaneous. You can now calculate changes in delta G, because what if the delta G does not go in the direction you want it to go? This is what a lot of chemical engineering is all about. You want to be able to change a reaction to go the direction you want it to go by changing conditions. And that also happens in synthesis in basic chemistry. There's two things you can do. You can change the temperature or the concentrations. We're going to look at temperature today because we already know the equation, and we'll look at concentrations in the next class. If you wanted to calculate delta G at a temperature other than 298, you can't use the table for delta G. So the question is, if delta G definitely changes with temperature because T is in the equation, the thing is, if H and S also changed, you would now have three variables. But what people have found for chemical reactions, H and S do not change very much with temperature. For example, if you take a reaction and heat it, the delta S of the reactants definitely will go up, but the delta S of the products also goes up, and it goes up by about the same amount. And so when you subtract, you still get the same delta S. That's an approximation, but it's a very good one because people have tested hundreds of reactions and verified it. So when you calculate the H and S from the table, those you can consider valid at any temperature, but you can only use the delta G values from the table at 298. So the question is, how do you calculate delta G at a higher temperature? Let's suppose you want to calculate delta G at 12,000 K instead of 298. Since you can only use delta G in the table at 298, the only way you have to do this is to use the Gibbs equation. You plug in the same H and the same S, but the 12,000 for the temperature. When you calculate delta G, you find out that it's now positive. So at 298, the reaction was spontaneous or negative G, but at 12,000, it turned around. It became non-spontaneous or positive G. Since it was negative at low temp and positive at high, there must have been a temperature in between where delta G was 0. We can calculate that by taking the Gibbs equation, put in a 0 for G, and solve for T. If you add T delta S to both sides first, and then divide both sides by delta S, you get that the temperature where delta G becomes 0 is always equal to H over S. And in this problem, it's 10,000 K. Why would an engineer want to know this? See, why do you heat a chemical reaction? You heat it in order to speed it up. But you don't want to heat it too much, because if you heat it to too high a temperature, you'll make it go backwards. So it's just like all of chemical engineering. It's a trade-off. You try to get the highest temperature possible that still fulfills the conditions of being able to synthesize the substance. The temperature where delta G is 0 is called the temperature where you get a change in spontaneity, because that's where you go from positive to negative or negative to positive. And as we said, the temperature where the spontaneity changes, which we derived, is always H over S. Now, because of the fact that delta G changes with temperature, you can generate a table that shows how delta G changes by what the signs of H and S are. If you look at this, there's four possibilities. You can have for H and S negative, positive, positive, negative, both negative, or both positive. And we're going to show that delta G changes in different ways depending on the signs of H and S. Now, the question is, do I want you to be able to reproduce this table? Yes. You're going to be able to look at it in your book, of course, so it's a little bit easier than you would normally have, but I still want to go through how you get this, because the truth of it is, if you just memorize all the little pluses and minuses, you're defeating the purpose. Because what I want you to do is use the Gibbs equation mathematically, and you can generate all of what I have written down here by math. So let's take the first case. Delta H negative and delta S positive, those are both the favorable signs. In order to do this, I want to rewrite the Gibbs equation a little differently. Instead of H minus T delta S, I want to put the negative in front of the T behind parentheses, so you're adding instead. I think it's easier to see that way. So let's suppose that you plug in a negative H and positive S. If you look at the second term, temperature is never going to change the sign because all Kelvin temperatures are positive. So if you take minus a positive in math, you're going to get a negative. And when you add two negative numbers, there's no way to get anything but a negative answer. So the delta G will be negative no matter what the temperature is. That means it's spontaneous. If you have two good terms, there's no way to make the reaction bad. This is the first case in the table where those signs of H and S give you a negative delta G at all temperatures. If you do the signs that are opposite so that they're both unfavorable, if you put a positive for H and a negative for S, minus a negative is positive. And obviously, if you had two positive numbers, you have to get a positive result. So delta G is positive at all temperatures. If you take two bad terms, you can't get anything but a bad result, which is non-spontaneous at all temperatures. And this is the second case in the table. The time when it gets interesting is if the signs are the same. The negative for H is favorable, the negative for S is unfavorable. And so if you plug those signs in, minus a negative on the second term comes out positive. Now if you add a negative and a positive in math, you know that you're supposed to subtract, and the sign of the answer is the bigger number. So it's going to depend on the temperature this time. If you use a temperature that's very small or low, it's always going to be a different cutoff for each reaction, but where delta G is 0. But if you're below that cutoff temperature, the second term is going to be negligible compared to the first term, and your delta G then is going to come out negative at low temperatures. So you can conclude that at low temperatures, in this case, delta G will come out spontaneous or negative. But as you raise the temperature, the second term becomes bigger and bigger, and eventually it will overwhelm the first term so that delta G will become positive and the first term will be less important. This is the third case in the table, and it's at low temperatures spontaneous and high temperatures is positive. This is the most common case in synthesis of anything in industry or chemistry, because what you're doing, for example, if you're synthesizing a drug, you're taking a bunch of small molecules and putting them together in a very complicated structure. So you're going from a state of disorder to a state of order. That's a negative S. But when you put small molecules together in chemistry, the reaction is usually exothermic, and so that's a negative H also. So in synthetic reactions, a lot of times what happens is you want to heat them in order to speed them up, but if you heat it too much, you'll switch the direction, and then you'll go backwards from how you want to do it. So it's always a trade-off. That's the case in the reaction that we were talking about earlier. The delta H and the delta S were both negative, and the reaction was negative at low temperature, 298, and it was positive at high temperature, 12,000. For the case where both signs are negative, you're going to get the opposite result, because the second term minus a positive is going to come out negative. So when you add these two numbers, It again depends on the temperature. If you're at a low temperature, the second term is going to be negligible, and the delta G is going to be positive, or non-spontaneous. As you raise the temperature, the second term, or the negative, is going to get larger and larger, and it will eventually overwhelm the first term, and the reaction will become negative or spontaneous. And that's the fourth case in the table, just what we calculated. We're going to talk about this table a lot in the next class, but this is really the basics of thermodynamics. You really need to know these signs well. The idea behind it is that the favorable signs here are in green for go, and the unfavorable signs are in red for stop. For H and S, the favorable signs are negative and positive, but those are what I said are only tendencies, because you can't tell whether the reaction is spontaneous from either one. They tend to make it spontaneous, but you have to consider both of them together in order to know for sure. But delta G is the final answer. As long as you know that delta G is negative, you know for sure that the reaction is spontaneous. In the next class, we're going to have two other columns that are final answers that are both related to delta G, and that will continue the study of thermodynamics into more stuff from chemistry.